Cyclic notation? Yeah.
So does it matter like which element we start with? Like I just noticed we started with A all the time. Like as long as you've got like a completed cycle within parentheses, does it matter?
You're right. It doesn't matter at all.
Okay.
I could have started with D and it wouldn't have
Okay.
mattered. The thing is you're gonna end up with a bunch of disjoint cycles at the end, right?
Okay.
Because you're gonna sort of build up the cycle and it's gonna complete. You'll go, okay, that's it. You'll say,
Mhm.
what have I not dealt with yet? And then you'll build up, a cycle that contains that element, and each
Mhm.
element is going to uniquely determine its cycle.
Mhm.
It's going to be disjoint from every other cycle.
Okay.
Does that make sense? So it doesn't really
Yeah.
matter what you start with because
Mhm.
you just have to build them all up anyways.
Okay. That's what I thought, but I just didn't know if it was kind of a specific rule with that.
I mean, you guys didn't take abstract algebra yet, have you?
No.
Okay. Yeah. So in abstract algebra, that's where you really start messing around with this stuff quite a bit. So, um,
That's next semester.
right, right. So all this stuff with like symmetries of the square and symmetries of the n-gons, that will kind of come back in full force, and you guys will just be like, oh man, no problem, right? These are, in fact, like these groups. I mean, we use the term group. These groups of symmetries are referred to as the dihedral groups. Um, so I mean, and they're pretty important in applications. And we're not just going to be looking at dihedral groups. We'll also be looking. I mean, we already in the last lecture I looked at that example of the tetrahedron, right?
Mhm.
Um, and those symmetries are a little bit different. And it's actually sort of hard to argue that there couldn't possibly be other symmetries with those shapes. I mean, it's possible to do it.
Mhm.
Argument isn't quite as elegant because it's like, okay, I see that you can like rotate around one of the points on the tetrahedron. I see that.
Mhm.
See how you can like flip along an edge like that. But how do you know that if I like combine a couple of those, that I don't get some new, thing that I haven't accounted for? Does that make sense?
Mhm. Yeah.
Mhm.
How do you know that combinations of those two don't somehow give us something that's not accounted for among those rotational, uh, or among those vertex rotations or the edge rotations?
Mhm.
And that's a little bit more nuanced. But for n-gons, did the argument make sense why there couldn't be any more?
I think
Mhm.
so.
Just based on like you take a vertex,
Mhm.
the images could there possibly be? Well, in places, and then the edge flipping, like you kind of highlight one of the edges and watch what it does.
Mhm.
So 2 times n is the most number of things that you could have. Well,
Mhm.
that's all we have. So
Yeah.
Mhm.
that's it, right?
Mhm.
Um, and that ends up being all there is. By the way, while I was lecturing, I mean, this always happens. I read through it carefully, and then as I'm going through, it's like I notice some typos sometimes, and there was a couple of typos that I had to fix after I did that. So I'm going to re-upload the thing again, and the next lecture I'll probably point out where some of the typos were, because I kept, like, I had the color on the usual side a few times, and I really want it to always be on the other side. Do you guys understand why I'm doing that, by the way? Like why I'm writing the colorings on the wrong side of the permutation almost?
Are you talking about when, because you were saying you don't want us to get confused with um, like composition of, is that
Yeah.
what you're talking about? Okay.
Because if I put the parentheses with the C in there, what are you going to tend to apply to that coloring first? Well, the rightmost permutation, right? You're going to tend to apply the rightmost permutation,
Mhm.
because that's what you do when you do composition of functions.
Mhm.
You apply the rightmost thing. But the way the book works, they always want you to apply the permutations in a left to right fashion.
Mhm.
And so And so to avoid that confusion, I'm going to put the coloring on the other side. Yeah.
Okay.
Does that kind of make sense? I mean, it's a
Mhm.
bizarre notation, but I don't really know how else to, and I don't want to just completely ignore what the book did and just do my own thing, because then if people go read the examples, they're going to be like, what in the world's going on? Hammett said that pi 2 operated with pi 6 is this thing, but it's not, it's some other thing. It's like, well, okay, that's if I was reading it right to left, whereas they're reading it left to right. So I had to use that notation. There was a couple of there was like one other typo I had to fix that I'll make reference to in the next one as well. But yeah. There was something else I was going to say. Oh, did it make sense to you? I mean, I don't want to make mountains out of molehills here, but did it make sense to you why I was like notating the permutations by pi in some case and pi twiddle in other cases?
Mhm.
I think so. Pi is just basically the permutation of the vertices, whereas pi
Uh-huh.
twiddle is the permutations that then come of the different the C's themselves,
The
the different
colorings
colorings
them,
Mhm.
the
themselves. Yeah.
colorings themselves.
hmm
Yes. And that's different, right?
hmm
I mean, one induces the other, right?
hmm
Permutation on the vertices gives birth to a permutation on all
hmm
things, but you can't act as if those are the exact same things. And the book
Right.
fortunately does. Just it just uses the exact same notation. And I think Dr. Fry would be passed out on the floor if he saw such a thing. So I mean, I just want to make sure that I'm not being cavalier with that sort of thing. I know you'll go take abstract algebra and it will be like uber rigorous. Okay, this is not the exact same thing of this. It gives rise to this. So I want to make sure that you guys are on the edge of correctness in that regard. So that made sense then why I was doing that?
Mhm.
Mhm.
Yeah.
Okay. What else? Any other specific questions?
I had a homework question.
Oh wow. Okay. From the next one?
Yeah, from homework 8.
Okay.
8.2 problem 4. So I know we did an example like this when Dr. Cook was here teaching, but this one just was slightly different, and I wanted to make sure I knew what was going on.
Yeah. Oh. Hey, didn't I actually prove the formula for um the general thing
When
in
I-
class? Like after he was gone? After I
that,
mean did I do that? Hang on, I'm gonna come jump in to this meeting so I can upload this thing. I proved the so-called Euler phi function formula, I thought.
oh yeah, I think
I mean,
yeah,
we can see it in
Mhm.
practice here as well.
yeah. Okay.
Yeah. Oh wait. Okay, so let me share this. But we'll go ahead and do this. This will be helpful. Oh man. Okay. How would you factor 670 or 630?
I got 2 times 3 cubed times 5 times 7 as the prime factorization.
Okay, so like 9, right? 9 times
Mhm.
9 times 7 times 10, which is 2 times 3 squared times 5 times 7, basically.
Yeah.
Mhm.
So, let's let M2 be the set of multiples of 2 in the integers from 1 to 630. Okay. And I don't know, what about M3? What do you think M3 is going to be?
The multiples of 3 in those
Yeah.
integers.
Okay, and then I have M5 and I have M7. Okay. Anything that is relatively prime to 630. So by the way, you know, phi of 630 is equal to the size, or it's equal to the number of integers, you know, n belonging to, oops, get rid of this, number of integers n belonging to the interval from 1 to 630 with what property? The property that the greatest common divisor of n and 630 is 1. Okay, the only way that that's going to happen, okay, that's going to happen if and only if an integer between 1 and 630 is not a multiple of 2 and not a multiple of 3 and not a multiple of 5 and not a multiple of 7. Okay, and that's an if and only if. Okay, if it, right? I mean, if it has a common divisor with a number that's bigger than 1, then it would have to be chosen from among these prime numbers that divide 630. Yes, it would have to have some of these as its prime factors. Okay, so if we can rule out any multiple of 2, 3, 5, and 7, we're in good shape, aren't we? You know what I'm saying?
Yeah.
Mhm.
So what do we want? What is it that we want to count?
Not M2 and not M3 and not M5. Not
Yeah. And not M3 and not M5 and not M7. Okay, which is going to be the size of the universe, which in this case is really easy to count because it's just the numbers from 1 to 630. And then we go the size of M1, M2, right, minus the size of M3, minus the size of M5, minus the size of M7, plus, you know, the pairwise intersections, right, plus, etc., minus, right, and we kind of know how this goes. Okay, so let me ask you, like, what is, okay, so first of all, the universe is easy. I'll count that. That's 6. Okay, what about M2? How many multiples of 2 are there in this universe?
630 divided by 2
Yeah.
or 315.
Okay, I would just leave it like that though. Might as well not describe
Okay.
a pattern if we don't have
Okay.
to.
That's how I was doing it when I was working on this one earlier. So
Yeah, 600, because what we'll see is something interesting happens that really hints at what's going on generally. Okay, what about M3?
630 divided by 3.
Yeah, minus 630 divided by 5, minus 630 divided by 7, right? Every seventh number is divisible by 7 in there. And so that's the number of multiples of 7 equal to or less than 630. And then what is, okay, what's the size of M2 and M3?
630 divided by 2 times 3.
Yeah. Oh, man. Right, 630 divided by 2 times 3. And then you start to see kind of a pattern emerging. So let me go over here. So watch, this is equal to, so think about this. I could like pull, apparently, okay, so like any pairwise intersection, it's going to be 630 over the product of those two primes, yeah?
Mm-hmm.
And then what about, and then I add in the triple intersections. And it's going to be 630. That means a multiple of all three of those, a multiple of the product of those things, right? So it's going to be 630 over the product of those three primes. And then it's going to be minus 630 divided by the product of all four of those primes. That's the last thing that's going to be there.
Mm-hmm.
Do you see?
Mm-hmm.
So so in the end, I can like factor out 630, can I? And what would be left behind? 1 minus a half minus a third minus a fifth minus a seventh plus what? 1 over 2 times 3 plus 1 over 2 times 5 plus you know, dot 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 plus let's just do 1 over 5 times 7. Okay, minus 1 over 2 times 3 times 5 minus dot 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 minus 1 over 3 times 5 times 7. Okay, and then plus, what's the last thing going to be? Plus
1 over 2 times 3 times 5 times 7.
Okay, and here's the big reveal. With all of our expertise in generating functions, we start to see, oh man, look at this. It looks like I do basically 1 minus 1 over any one of the singular primes plus, and like if there's 2 primes, I'm basically multiplying together 1/2 and 1/3 and 1/2 and 1/5. Yes?
Mm-hmm.
And then if I have 3 primes, it's like I'm multiplying together 1/3 and 1/5. But that came with a minus sign. So that ought to set alarm bells off and make you say, oh man, it looks like what I did is I took 1 minus a half and I multiplied it by 1 minus a third. And I multiplied that by what?
1 minus a fifth.
Yeah, 1 minus a fifth. You see, if I were to multiply all this junk out, do you see that I would get exactly all that junk that's up there?
Mm-hmm.
I would get a 1, and then I would take 1s from the other. Oops, I have one more factor I'm missing here. 1 minus a seventh, right? I would get 1, and then I would take them negative half, and then 1s from the other, or negative third, and then 1s from the others, etc. Or I would take, you know, 1/2 and 1/3, which would make it a plus 1 over 2 times 3, and then take 1s from the others. Yes, you can kind of see how that would play out if we were to multiply that thing out. So that's a nice formula, right?
Mm-hmm.
And that hints. So let me just let me go on another page. So so what this is equal to 630 times the product. What were we doing? Where did that 1/2, 1/3 junk come from? Where did that junk come from? Well, it came from the primes that divided 630. Know what I mean?
Mhm.
Mhm.
Really what we had here was it was the product over primes that divide 630. That's what that notation means, divide 630. And by the way, these p's right here are primes. So it's the product over primes dividing 630, 1 minus 1 over p. And this, because you guys are both staunch probabilists at this point, this ought to also set off alarm bells. The fact that I have 630 right here, which is the total number of numbers, yeah?
Mhm.
And this is and yet this is the total number of things that are relatively prime. That means if I wanted the probability of a randomly selected number between 1 and 630 being relatively prime to this, the 630 would cancel. Yeah?
Right.
I would take this count and I would divide it by 630. And so what does this product necessarily have to be? That, what is it? Go for it, Katie.
Oh, the probability that any random number is relatively prime
Yeah,
in that interval.
that a random number in the interval from 1 to 630 is relatively prime to 630. Yeah. And so that, and incidentally, that formula generalizes, and that's kind of what we were doing in class at some point. So like phi of n, right? The Euler phi function for n is just going to be n times the product over primes dividing n, 1 minus 1 over p. Okay, so that formula generalizes to things that aren't just, 630, but could be anything at all. It's kind of interesting. Do you kind of remember doing that in the notes at some point?
Yeah, yeah. No, I
Mhm.
flipped back and I had notes on that. It had been a while and forgotten about that.
Yeah. Yeah, this is important enough. I mean, and it will come up again, and it will come up again in abstract algebra. The Euler phi function will. And if you took number theory, or if you ever take number theory, this is front and center for a long time in that class. This idea of being relatively prime to something is huge in a variety of mathematical contexts. So it's nice to have this formula in your back pocket. Yeah. And we can prove it by inclusion exclusion. Well, what else? What else? You guys have anything else?
That's all I had for now.
Yeah, that was my only question too.
Oh, wow. Okay. I don't know. I mean, I may have lied a little bit last time. I think I said I assigned every problem in 8.2. I don't think that's exactly true, but I did assign a lot of them. I do think that 8.2 is the most important section in the entire book, because it really just drives home a lot of stuff that we've been doing for sure. Yeah. Well, anything else on your minds?
Out of curiosity, so you mentioned that when you were making the YouTube channels, you wanted to have like a more creative name, but it wouldn't let you. And we were wondering what the more creative name would have been for that.
Oh, man, I don't know. I think I gave up trying to think about that because I realized pretty quick I wasn't going to be able to do it. But
Mhm.
I don't know, something with the, something. So I don't know, some permutation of my name probably or something like that. So yeah.
Okay, just
Has
wondering.
YouTube been working all right for you guys?
Yeah,
Yeah, it's been great.
That's good. Have other people been using that at all, or no?
I think so.
Like other professors?
None
Um,
of my other professors have, but
I don't think so. I think some that I don't necessarily have been using that from what I've heard, but
Okay. Seems like a pretty good option. I mean, it actually uploads faster. It, you can adjust the quality level based on your, based on how fast your internet service is.
mhm.
Do you have the option to download the videos? I don't know if you do or not.
I
I'm
don't
not
know if
sure,
I do,
I'm not
but
sure.
but it just seems to have a lot more flexibility. Somebody actually disliked one of my videos the other day. I was so hurt. No, I'm just kidding. I actually laughed at that. Um, it was in one of my other classes, though. So,
Okay.
yeah. I mean, hopefully again, I don't ever know how much detail to go into, but hopefully the lectures are kind of making sense.
yeah.
Mhm.
Um, I don't spend a lot of time doing board work on those ones because the notes are so complete.
Mhm.
But eventually there will be a lot more board work, if you will, when we have a fully developed theory of how to count these things.
Mhm.
And we'll be doing examples and we'll have all these tools to be able to count really complicated things. It'll be fantastic. So, yeah.
How's the hunt for new professors going?
What's that?
How's the hunt for new math professors going with all this craziness?
It's going pretty well. We have a teaching presentation tomorrow. We did another interview via Zoom.
Mhm.
We have a teaching presentation tomorrow.
Okay.
Were you guys I thought they were going to try to invite some students. Um,
I haven't heard anything about it.
Yeah, I don't think so.
well, let me look into that. That would probably be a good idea, but you know, so yeah, there's a teaching presentation tomorrow afternoon at some point.
Okay.
Um, so, but all the initial interviews have gone pretty well.
Okay.
So yeah,
Cool.
all right. Well,
Mhm.
anything else?
I think that's
I don't
it.
think so.
Well, cool. Uh, I have some catching up to do on my grading. I've gotten behind on that, but hopefully I'll get caught up on that pretty soon. And then I'm hoping this weekend will provide an opportunity to catch up on some of that. So then we'll just keep on going.
Mhm.
All right, guys.
Thank you.
Thanks, Dr. Hammer.
Yep.